Hello everyone, welcome back. Today we are tackling a classic binary search tree problem, Leetcode 230, kth smallest element in a binary search tree. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given the root of a binary search tree and an integer k, and we have to return the kth smallest value, one indexed, of all the values of the nodes in the tree. For example, the sorted values for this tree are 1, 2, 3 and 4, and here k is equal to 1. So we will return the first element, that is 1, as the answer. Or if k was equal to 3, we would have returned the third value, which is 3, as answer. And how do we get these nodes in the sorted order? Well, the secret lies in a fundamental property of the binary search tree, which is if we traverse the binary search tree in order, we will get the nodes in the natural sorted ascending order. And in the Inorder traversal, we go from left, root and right. So we traverse the whole left subtree first, then the root node and then the right subtree. For example, for this tree, we begin at the root node, but we can't visit it yet, as the rule says that we must go to the left side first and then the root. So we go to the left where we see node 1 and again we try to go to the left, but node 1 has no left child. So we visit it and this is our first smallest element, and after visiting it we follow the final part of the rule, which is go right, where we see node 2 and again follow the same process by going to the left, but node 2 has no left child. Hence we visit the root, which is node 2, and it is the second smallest element, and then we try to go to its right child, but it has none. So we have completely finished the left subtree. So we go back to node 1 and then back to node 3, and now since we have finished the left subtree of node 1, we visit it and go to its right where we see node 4, and since it also doesn't have any left child, we visit it and try to go to its right, but it has no children, so we are done with this path as well. And finally our Inorder sequence will be 1, 2, 3, 4, and here k is equal to 1, so we will return 1 as the answer. Similarly, if k was 2 or 3, we would have returned second or third element from the list and so on. But how do we translate this insight into the code? The most straightforward or naive way is to do exactly what we did in the example walkthrough. First, we can perform the full Inorder traversal of the binary search tree. And as we visit each node, we add its value to a list. For example, for this tree, we will get the sorted list as following. And once we have this sorted list, the problem becomes simple. The kth smallest element is just the element at index k-1 in our list, as the kth value is 1 indexed. For example, here k is equal to 3. So we look at index 2 in the list and return element 3. So this approach is simple and it works, but the time complexity of this approach is O of n, where n is the number of nodes in the tree, because we traverse the tree once to build this list, where we store all the n elements in the list, which results in the space complexity of O of n, and it is a perfectly valid solution, but it does more work than necessary. We build the entire sorted list even if k is very small. For example, if the tree had 1,000,000 nodes and we want only the second smallest element, we are still building the 1,000,000 element list, which is not optimal. So, can we do better? And the answer is yes. We don't need to visit and store all the nodes. Since we only care about the kth node in the sorted sequence, we can stop our traversal as soon as we find it. Instead of adding a node to a list, we can count how many nodes we have visited during the Inorder traversal, say using a separate counter variable, incrementing it each time we visit a node, and continue this process until it equals k. However, a slightly cleaner way is to use k itself as a countdown. So every time we visit a node, we decrement the count, and when the k hits 0, that means the current node is the kth node, and that will be our answer. So here, for example, we start at the root node 3 with k is equal to 3. And since it has a left child, we go to the left where we see node 1, and node 1's left child is null or non-existing. So we visit it, and this is the first node visited. So we decrement the count of k to 2. Now we go to its right where we see node 2 and try to go to its left child, but it doesn't exist. So we visit it, and this is the second node visited, and hence we decrement the count of k to 1. And now we are done with the left subtree. So we return to 3, and back at 3 we have finished the entire left branch. So now we visit it and decrement the k to 0. And now since k is equal to 0, we have found the answer, which is current node's value, which we can now return and stop the traversal immediately. And while the recursive approach is easy to understand, it has function call overhead and can be awkward to stop cleanly the moment we find the answer. A much cleaner and more common way to handle this, especially when we need to stop early, is to do it iteratively using our own stack instead of recursion stack. The strategy will be to manually simulate the Inorder traversal where we go to the left, then the root, and then go right. So let's again trace this example with k equal to 3. And again we start at the root node, but we can't visit it yet. We should go to the left. So the first phase is to go as far as left as possible from the current node, adding each node to the stack along the way so that we can process it later. Here we start with node 3 and push it onto the stack and go to its left child 1 and push it onto the stack. And now since we can't go left anymore, we process the node from the stack. So we pop out 1 from the stack, which we identify as our first smallest element. We then decrement k by 1 and k is now 2. And after visiting or processing this node, we move our current pointer to the right child of the node we just processed. In this case, now the current node is 2. So we push it onto the stack and again repeat the process where we go left, but 2 has no left child. So we pop the node from the stack, and this is the second smallest element, and we reduce k to 1. And now we try to go right of node 2, which doesn't exist. So we visit the next element by popping it out from the stack, which is node 3, and decrement the k by 1, and now k becomes 0. And since k is equal to 0, we immediately stop and return the value of the last node we popped out, which is node 3. And notice that we found our answer without ever visiting the node 4. Now the time complexity of this approach is O of h plus k, where h is the height of the tree, because it takes O of h time to travel down to the smallest element, and then we visit k elements to find our answer. In the average case of a balanced tree, the height will be log of n. So the time complexity becomes O of log n plus k. But in case of a skewed or unbalanced tree, the height is n. So the time complexity becomes O of n plus k, or simply O of n. And the space complexity will be O of h, determined by the depth of the recursion in case of the recursive solution, or the size of our explicit stack in case of the iterative solution. For the balanced tree, the space complexity will be O of log n, and for the unbalanced tree, the height is n, leading to the worst case space complexity of O of n. This is still a significant improvement over the naive approach, where the guaranteed space complexity was O of n, as we were visiting all the nodes. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, we initialize an empty stack to help us with the traversal, and the current pointer that starts at the root of the tree. Now we enter the while loop, which runs as long as current pointer is not null or the stack is not empty. This ensures that we visit every necessary node, and inside the loop, our first job is to find the smallest node in the current subtree. For that, we have to move towards the leftmost point of the tree. So we create another nested while loop and go towards the left until the current pointer is not null. But before going to the left, we should push the current node onto the stack so that we can process it later. Now, once we have reached the leftmost node, the current pointer becomes null and the top of the stack holds the next node to be visited in the inorder sequence. So we pop that node out and process it. That is, we decrement the k by 1 and check if k is equal to 0. If it is, then the current node is the kth smallest node and we immediately return its value. But if k is not yet 0, we continue with the inorder traversal by moving towards right. So we set the current pointer to the right child of the node we just processed and repeat this cycle until we find the kth smallest element. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.